So, good morning, everyone. Thank you very much for being here today. I would like to thank first Professor Sejik Pasha, for accepting to be the president of my jury. My sincere gratitude goes for Zita Valley and Catherine Azaro-Fontaine for accepting to report my thesis. And finally, Marie-Cécile Alvarez for always being here for the last years of my thesis, seeing my work for the CSI, but also accepting to be examiner for my work. So, I would like to start with a short image. Imagine a small island far from the mainland. Its electricity mainly comes from diesel fuel transported by boat. When the sea is rough, or the deliveries are delayed, people face shortages, high prices, and instability in their electricity supply. Now imagine the same island powered by the sun, the wind, and the winds, using local renewable energy sources, stored efficiently, and managed intelligently. That's the vision that inspired my work. My name is Haje EBNOU, and over the past 3 years, I have been working on this subject at the intersection of energy systems, optimization, and data science. Today, I will present the main result of my work, going from the deterministic design stage to the scenario generation method, then the uncertainty analysis, and finishing with a stochastic design that integrates uncertainty into the optimization process. So let's dive into it. I would like first here to show the energy consumption by source in France, where we can see that we have a rapid growth of energy consumption until the 2000s. After that, we have the stability, and then a decrease of the energy consumption. But another thing to notice is that we have a great reliance on nuclear and fossil fuels, which brings a negative environmental impact. One solution is to deploy renewable energy sources. Renewable energy sources have some positive points, such as their sustainability. They bring a low environmental impact, and especially for the isolated places, they give us the opportunity to be independent from the fossil fuels. We have some challenges related to it, which are the intermittent nature, the fact that we need storage, and finally, the high initial investment costs. So, to resolve the two first challenges, which are the intermittent nature and the storage dependency, one solution is to combine renewable energy sources, which brings me to the idea of microgrids. Microgrids are small electrical systems composed of renewable energy sources, storage, and it can or not be connected to the main grid. They have some advantages, which are the reduce of the transmission losses because they are always very close to the consumers. They improve the reliability. And finally, and especially, they are environmentally friendly systems. They come with a high investment cost. Also, we have a negative point, which is the complex control and management because of the fact that we have several renewable energy sources that we need to manage at the same time. And finally, because in our study we are interested in remote areas, islands, for example, we have some difficulty to maintain and operate those microgrids. This brings me to the OPTILE project, which the goal is to assess the feasibility of maximizing the use of renewable energy sources. And we have two parts in this project. We have first the energy-based approach, which is part of my thesis, and second, a real-time simulation to verify the stability of the electrical network. Some partners in the project, we have some partners in the project, academic and industrial partners, as you can see in the slide. For the case study of this thesis, the project chooses La Réunion Island, which is an isolated French island located in south of Indian Ocean. It has some high dependency on imported fossil fuels, but also it has a great potential of renewable energy sources. which comes with the fact that we have a strong natural variability, resource variability. A quick overview on the background of the work. After doing the literature, we noticed that we have extensive work on microgrid design, but mostly they are deterministic, based on historical data to do the design. However, emerging studies on stochastic approaches have been seen. For the stochastic approaches, normally we generate scenarios. One approach is to generate scenarios for the time series used in the design problem. So the scenario generation in the literature are often oversimplified. Correlation are not taken into account. And also another research gap is the fact that we have a limited integration of uncertainty optimization, but also sensitivity analysis are rarely performed. So this takes me to the thesis objectives. We want to develop a robust methodology for microgrid design to ensure cost effectiveness and reliability. And finally, to assess the uncertainty impact through sensitivity analysis. This takes me to the scientific contribution of this thesis, which are first, we use time gun, which is a method that I will go into details later in this presentation, to generate long-term synthetic scenarios. We did a comprehensive sensitivity analysis. And finally, the integration of uncertainty into the stochastic process design. So the first part of my methodology is about the deterministic design, where I design the microgrid by choosing the optimal component sizes of the components that are in the microgrid. So we studied the system that looks like this, where we have solar, offshore solar PVs. We have some wind turbines, offshore wind turbines, conventional generators, such as diesel generator in our case, and some energy storage. We took some batteries for this study. We have some consumers which represent the island. And finally, a control center to manage everything together. The goals here are to maximize the offshore renewable energy sources, balance multiple objectives that are cost and reliability, and finally, develop an effective energy management system to respect the constraints of the electrical system. And to do this, we begin by modeling the component, the different components that we have in the microgrid, energetic modeling for the renewable energy sources, but also for the battery diesel generator, and also economic modeling of it. We relied on the literature to do this part. Two evaluation indicators have been chosen. First, the loss of power supply in hours, which is a measure of the reliability. And second, the levelized cost of energy, which is the average cost per unit of electricity generated. This indicator we have in it the capex, the opex, the replacement cost, but also the true cost. After modeling the component, now we can formulate the optimization problem. So we choose the design variables such as the battery capacity, the diesel generator, the nominal power of the diesel generator, and the number of PVs and wind turbines that we need to satisfy the consumption. Two objective functions are chosen. First, the levelized cost of energy and the loss of power supply in hours. Those are subject to constraints that are very open in our case. We didn't put any range for those constraints, but we can say that the constraints are the maximal and minimal limits of the decision variables. After formulating the problem, we can then integrate the energy management system that we developed. This part is based on rules which are defined based on the state of charge, power demand, and generation capacities. The goal is to maintain energy balance at all times by also respecting the diesel generator optimal functioning. And to do this, first we use the renewable energy first. After that, we can charge or discharge the battery if we have a deficit or a surplus. And at last resort, we start with diesel generator, only when necessary, so to minimize the environmental impact. So integrating the energy management system with the optimization problem, we can then, Before this, I wanted to show also the conception studied in this part. And this conception is taken from EDF La Réunion. And it represents the conception, the power demand from La Réunion, where here we can see a clear seasonality. And if I zoom into it, I can see here for 7 days that we have a clear pattern where we consume more in the day than in the night. So this is the conceptual study. If I want to show the functioning of my energy management system, I can put here first the conception. The goal is to satisfy this conception. We can add the renewable energy power, where we can see here that it doesn't satisfy the conception all the time. But I choose those 7 days only to show, in fact, the functioning of all the sources. Then we have the battery and the state of charge, where here we doesn't rely a lot on the battery, but this comes with the fact that the diesel generator is already starting. So we rely more on the diesel generator than the battery. So this is the functioning of my energy management system. After this, I can compute the optimization problem. So computing the optimization problem with the energy management system, we obtain a Pareto font here, which represents a trade-off between reliability and the cost. And each point represents a configuration, an optimized solution. Then I show the number of PVs and wind turbines, where we can see that at this reliability, in fact, here we are less than 5% for the reliability, meaning that we satisfy 95% of the consumption already. So you can see that the sizes of the PVs and wind turbines are stable at this point. If I integrate the battery, we can see here that we rely more on the battery than on the renewable energy sources. The battery is very proportional to the cost. And finally, the diesel generator, which is almost also stable. It increases a little bit, but we rely more on the battery and the surplus of the renewable energy sources. So we can have here a clear cost reliability trade-off, which means lower APSH, which means better reliability, require more PVs, wind turbines, but also storage capacities. The next part is to study two configurations. So I wanted first to see if I can, if I want to compare between two configurations. First, using only diesel generator, and then using diesel generator and adding renewable energy sources with storage. And I obtained for this only diesel generator this Pareto font. The same, a trade-off between reliability and the cost. And if I put the Pareto font of renewable energy sources plus storage plus the storage plus the diesel, I obtain this Pareto font, which is clear that it's better than the fact that we rely more only on diesel generators. We have a decrease of the cost, but also an increase of the reliability. And I can also say that we have a decrease of greenhouse gas emissions because we rely less on diesel generators. Another figure here is to compare between the number of diesel generators chosen for the studies, for the two configurations. And we can say here that the diesel generator with the renewable energy sources and storage will decrease the number of diesel generators. So including renewable components significantly reduce both cost and reliability losses compared to diesel-only systems. To conclude this part, we can say that hybrid microgrids outperform diesel-only systems They bring lower cost, better reliability, but also they reduce the greenhouse gas emissions. To put this into context, we obtained for the levelized cost of energy 0.29, the range between 0.29 and 0.31 dollar per kilowatt hour. And to put this into context, to compare it to other electricity costs in islands such as Hawaii, it is very consistent in fact, with the fact that it is very close to the cost for Hawaii. So we did a deterministic design, which is based on historical data. And the next part is to use a method for generating scenarios to model the uncertainties related to time series. After that, it can enable us, after generating the scenario, to take into account the uncertainty into the optimization. Now I will go to the next part of the second part of my methodology, which is about the scenario generation method. We all know that integrating renewable sources adds strong variability and uncertainty. But also another thing to say is that planning requires long-term scenarios for resources and demand. After seeing the literature, we can say that existing methods, we have existing methods such as traditional methods, Markov chains or Monte Carlo, fail to capture complex patterns. But also, they don't take into account the correlation between the sources or the autocorrelation. So we wanted a method that can offer us this possibility to take into account the correlation. And we choose TimeGAN. TimeGAN offers a deep learning solution, but is used often for limited time series, short horizons. So we want to adapt this method to apply it to generate long-term scenarios. And we modify it by adding the decomposition, the reconstruction, and finally the validation of the scenarios. A quick talk about the TimeGAN. TimeGAN is a deep learning method introduced in 2019. It is an extension of the generative adversarial network, which is used normally for images. And it's composed of 4 neural networks, where the two very interesting neural networks here are the generator that produces the synthetic scenarios and the discriminator that distinguish between real data and synthetic data. So I take this method and applied it here by adding another blocks. So my method is based on first doing a frequency analysis to see the different peaks of seasonality that we have in the original data. Then we use a decomposition where we have 2 methods here in the decomposition. After that, we do the data preprocessing, and then we use TimeGAN to train the model for an amount of time. After training the model, we can use the generator and the recovery to generate as much synthetic scenarios as we want, do the composition, and then validate the scenarios. I will not go into details here, but I will take any question that you have later on this part. This method has been applied to 3 time series, which are first the electricity demand, PV projection, and wind turbine. In fact, for the PV and wind turbine, we generate scenarios from natural resources, then we calculate the power using the modeling of the PV and wind turbine to obtain the power of it. For this part, I will only focus on the electricity demand to show you the results. But I can also answer any questions that you have related to other time series. So to use the method, it is very simple. In fact, I go by using the original data, give it to the generation method, and then after a certain amount of time of training, we can generate the scenarios that we want. This is a quick example of it. But if I go here, we can show here 5 years of data, where the synthetic in red and the original in blue. We can see that we don't see as much the original here in blue, but we can see that the seasonality is conserved. This is because of the fact that that we conserve the seasonality as deterministic. I want to show here a rare event where we have a minimal conception, and I will show you later on the matrix the problem here. Then I show in the right side of the slide 7 days of conception, where we can see that the pattern is clearly repeated. We have, but they are not the same, which is the goal. If I wanted to have the same time series, I would not I would not use the method to generate scenarios. So this validation ensures that the generated scenarios are similar to the original data, but it's not enough. We need to have other metrics. So other statistical metrics such as the minimum, maximum, mean, standard deviation values, and also the correlation that we wanted to conserve from the original data. For the maximum mean value standard deviation correlation, you can see that here that the error is very minimal. We have a lot of differences between the original data and the synthetic data. But for the conception, we have here the minimum value that differs for the synthetic than in the original. This comes from the fact that what I show you later earlier in the time series, where we have a rare event where we have a minimum value that the timeline cannot replicate. So this can make us say that we have difficulty capturing rare events, but overall, the metrics validate the synthetic scenarios. Another validation is about the distribution. So here I put the original distribution of the constellation and the distribution of the synthetic scenario. We can say that they are very close, not the same, but very close. So overall, this also validates the synthetic scenarios compared to the original ones. A final validation is about the FFT, the fast Fourier transform, where we can have some frequencies that are replicated, but other frequencies that are not replicated with this method. So some improvement can be done, but overall we accept, in fact, the generated scenarios for us are enough to model the uncertainties. To conclude this part, I have developed this approach especially for La Réunion Island, but it can also be transferable to other regions. In fact, in the OPTILE project, they are applying this method to other places and other case studies. This method has some limitations, such as the high computational time, but also the fact, as I have shown earlier, the fact that it can underrepresent the rare events. Next, after generating the scenarios, we can then use it as input for system design to do a sensitivity analysis on the deterministic design, to evaluate how uncertainty impacts cost, reliability, and optimal configuration. So this takes me to the second part of my presentation. So for this part, I wanted to use the scenario generation method with the deterministic design, the result of the deterministic design that I obtained earlier, and then combine it with the uncertainty analysis that I will show you here. So the goal of this uncertainty analysis is to assess the sensitivity of the deterministic problem. We do this to justify the need for stochastic design. In fact, one thing to say about the stochastic design is that it takes a lot of time. So, and also it takes a lot of time. So we want to justify the fact that we do it in fact. So we justify it by doing a sensitivity analysis on the deterministic problem. And we do this by first using the historical data that we have, use the proposed method to generate scenarios from historical data, PVs, wind turbine conception, and apply those scenarios finally to the design problem to see the impact of the design. And we do this by using two approaches. First is what I call performance assessment, where I do an optimization with the historical data, and then I vary the scenarios to see the impact on the Pareto front that I obtain from the deterministic design. The second approach is the comparative optimization, where I do an optimization with the historical data. Then I do optimization with every scenario so that I can compare not only the Pareto front, but also the design variables, the components. So this is the first result of my performance assessment, where here I obtain in blue the original Pareto. And then we have three scenarios, three impact scenarios here that I show in the same figure. I plotted only three here to show you the variation of it. We can have one scenario that is more expensive in yellow, another one less expensive in green, and the last one that is very close to the original Pareto. This shows us clearly a variability, that the variability of renewable energy sources affect both cost and reliability effect. So if any future happen where we don't have this, it's not the same as historical data, the optimal configuration are not anymore optimal. I selected 8 points here to go deep into the analysis. Yeah, 8 points here. And then I put the 8 points here in red for the LPSH and the box plot that highlight the uncertainty. But every box plot highlights 100 scenarios, the results of 100 scenarios. So we can say here clearly that it changes a lot. It varies from one point to another, where sometimes we have the scenario, for example, for the point 4 in the middle, the original, the optimal point here in the middle. And it varies, the scenarios are very varying here. But it differs from one point to another. Sometimes it is more than the scenarios, and sometimes it is less. So this also shows the variability, that the variability of renewable energy sources affects the reliability very much. For the levelized cost of energy, we do the same analysis. We can say also that we have a great variability, but it is very stable for the SCO. Even though we can see that the optimal point is not anymore optimal impact for the other scenarios. So those box plots highlight the sensitivity and robustness of the selected 8 solutions under uncertainty. Next, I will show the result of the second approach, which is the comparative optimization, where we do the optimization with the historical data and we obtain this original Pareto in black. And then the synthetic scenarios are here in colors. So we can say that the optimal Pareto front is not the same for all the scenarios. So each scenario leads to a slightly different Pareto. So this illustrates the variability of optimal solution under uncertainty. This makes me, I can say by seeing this that the deterministic design is not enough, in fact, it's not optimal. Another analysis that I wanted to do, I wanted to compare between the LPSH min, where we have the conception satisfied at all time, so 100% satisfaction, and the LPSH max, where we don't satisfy the conception. 5% of the conception is not satisfied. And for this, I wanted to show the different variables. So first here, I show the number of PV panels, where we have in blue the conception is satisfied at all time, And in red, this conception, 5% of the conception is only satisfied. So we can see here a clear variability from one scenario to another. So if I go here, I have the original data, and here I have the other scenarios. For every scenario, we obtain a different configuration for the PV panel. For the diesel generator also, I wanted to show it, even though it is more stable. It is more stable than the PV panel, but also it shows some variation. The third component is the batteries, where we can see also the variability, more for the LPS min than for the LPS max. And finally, the number of wind turbines, where also we have a great variability. In fact, those results can make us say that PV, wind turbine, and battery capacities show high variability across scenarios. If I change a scenario and I do the optimization, I will not have the same size of the components. So it makes me say that we need a stochastic design to obtain solutions that are realistic, but also close to the reality. Yes. To conclude this part, scenario variability affects both cost and reliability. We can say also that the deterministic design gives us a good baseline, but is not robust, because anything can happen in the future. We will not have the same cost or the same reliability. Doing a comparative optimization between the scenarios and the original data, we obtain similar Pareto shapes, but shifts occur between scenarios. This highlights the impact of uncertainty on the optimal configuration, but also on the different Paretos. So next, to handle the uncertainty within the optimization process, we move from the scenario evaluation to the scenario integration by doing a stochastic design where we integrate the scenarios with the optimization problem to ensure robust and reliable designs. A quick drink for me before continuing the presentation.
Be comfortable.
So the last method here is about the stochastic design, where we integrate uncertainty into the optimization process. And we do this by formulating the problem. So the goal is to find a microgrid design X that minimizes the expected total cost. So we formulate the problem, the two objective functions, by taking the expected total cost for every objective function. This is based on constraint, also subject to constraint, that is a function indicating the state, the system state, based on uncertainties. One question to answer is how much scenario do we need to do to satisfy, in fact, to take into account the uncertainty, but have good results for the designs. I wanted to answer this question by adding progressively the number of the scenarios. So I do first an optimization, the orange optimization that we have, a deterministic optimization. Then I add 3 scenarios. After that, 10 scenarios, and finally 100 scenarios. A slide, we can see that we have the more that we integrate the scenarios, the more that the cost increases, which is very normal, if I can say. But I can notice also that the time computation increases also with the number of scenarios. So the question of how much scenarios do we need to do a realistic design? In fact, in the literature, it says that we need as much scenarios as the objective function. In fact, if I can just explain it very quickly, the change between the objective functions is the answer of this question. In fact, if the objective functions change, a lot, we need to integrate more scenarios. But if it doesn't change that much, we can accept an amount of scenarios that is enough for us. And in this case, so it is a personal choice here. I choose 10 scenarios because, and I can justify it by the fact that the Pareto here for the 100 scenarios and 10 scenarios doesn't change that much. So to have less time, because maybe in the future we can add other uncertainties, but also other objective functions, we accept 10 scenarios here for 2 hours to do more studies also. A quick comparison between the stochastic front and the deterministic front, where we can see that we have an increase in the cost. But this comes from the fact that we have better reliability in fact. We take into account several conditions. The results for the stochastic compared to the deterministic design for every component. We can see that here we have more battery capacity for the deterministic design in red, and for the stochastic design, it is less in this part, but it's more here if you want to have zero, if you want to satisfy all of the conception. The diesel capacity here is more for the stochastic design, so we have more diesel generators in the stochastic design than in the deterministic designs. For the PVs also, we have more PVs in the deterministic design than in the stochastic design than in the deterministic one. And finally, for the wind turbine, we have it is very stable at this point, but we can say that the stochastic design here, we rely less on wind turbines than in the deterministic part. This comes with the fact that we have a lot of variation in the wind turbines. So we want something more stable, such as PVs, but also batteries and diesel generators. The summary of it, we can say that considering uncertainty results in larger storage, less diesel dependence, and a wider range of renewable configuration. I wanted to show also the Pareto front with the component design. And if I want to compare this to the deterministic design, we can see here that the diesel generator here is more stable than in the deterministic design. In fact, in the deterministic design, when we increase the cost, so we increase the reliability, we rely on diesel generators and batteries. But in the stochastic design, we rely more on the batteries and renewable energy sources than on the diesel in this after 5% of LPSH. A last result for my presentation here is to compare between not only the deterministic Pareto front with the stochastic Pareto front. So I do the same thing that here, I do the optimization with the deterministic Pareto front and the stochastic Pareto front with 10 scenarios. And then I do a sensitivity analysis. First, I do a sensitivity analysis with the deterministic Pareto front. So I vary the scenarios, 100 scenarios. I can see clearly that we have a great variation here. And the cost is very stable at it. It is very close to the deterministic and the stochastic Pareto fronts. And if I do the same sensitivity analysis on the stochastic Pareto front, I obtain those solutions with those solutions that demonstrate greater relevance, which are the fact that, okay, I obtain an optimal configuration. Then one future happen. I will have less cost, but also the same reliability compared to the deterministic part, where if I choose one optimal configuration here and a future happen, the result will shift a lot. So we can say that stochastic approach demonstrates greater relevance for our case study. They provide more robust and adaptable solutions. To conclude this part, a stochastic design framework was developed for long-term viability. I can say that stochastic designs are more robust than deterministic ones because they take into account several possibilities, but they come with a higher investment cost, but better reliability and lower sensitivity, as shown just before. Next, we can extend the analysis with risk metrics, but also add some objective functions towards smarter, cleaner, and more adaptive microgrids. To conclude my presentation, this thesis focused on the optimal design of an isolated microgrid, and we do this by first doing a deterministic approach, which is the baseline, where we have a cost reliability trade-off. After that, we generate the scenarios from the method that the framework that we developed. And then we can see the impact on the sensitivity analysis. And finishing with the stochastic design that give us more robust solutions by taking into account uncertainties into the design process. This work can be extended can be improved by, for example, doing an advanced scenario generation that includes climate change projection, using finer time resolution, and also extend the objective, adding an objective function such as the greenhouse gas emissions, the social impact, and so on. Another perspective also very interesting is the fact that we can add more uncertainty sources, such as the fuel prices, the technology evolution, and so on. Finally, real-time validation is also required here, and it will be done in the next part of the OPTILE project. Thank you very much for your attention.